Hello everyone, this is Satvik, and this video we will discuss the next topic in our buffer overflows episode, which is rewriting your instruction pointer. So in the previous video we did stack overflows. We actually rewrote uh, some of the other variables in the stack or in the buffer and try to bypass the function. And this is our code for this example. Let me enlarge this a little bit. So you can see we have a main function which is calling read name. So read name is just reading your name, which is name, and you can see gets. So gets is a vulnerable function here, which is reading your name. So gets reads the content which is more than required. So here the name size is 10 bytes, but you give like 11, even your function will read. And the important function here is like a win function. So this is a typical CTF problem, like a basic or easy CTF problem where there will be a function. I'll tell you how you can identify this function without going through the source code as well, because in some challenges you'll not get your source code. They'll just give you a binary, the compiled version of this code, and you need to identify what to do. So our main goal is to run this win function, which is not being called here. So how you actually do is, so instruction pointer holds the address of the next instruction to be hold. So for example, if it's like a pointer which points to the next one. So if you take a queue in real time, so the instruction pointer is something that mentions who is going to be the next one. So if we are successfully able to rewrite the instruction pointer with the win function, then you can actually control this instruction flow and run the function that you want. So this can be typical because in some embedded systems, there are a lot of functions which call the bin bash using the system of call. And sometimes if you are able to call that function, then you can get your shell. So we'll discuss more about that in some upcoming videos, like where we'll discuss red to lepsy and all. So before that, let's see what happens actually and what we want to do. So this is how a stack looks like. So whenever you call a function, a stack is assigned. So it can be for anything. So first, the foremost step will be the EBP and ESP. So EBP is your base pointer. So stack has a base, and the ESP is holds the. So if you keep adding the values, your ESP keeps going up. But here in OS and all, computer systems and all, your stack grows downwards. So if you typically learn the concept of what a stack is, most of the examples teach you it goes upward or it grows upward. But here the stack grows downward. So whenever the first function is always going to be, the first assembly function is always going to be like push the EBP and the ESP. So E means EBP and ESP, or EIP refers to the 32-bit. RIP, RBP, RSP refers to the 64-bit. So we will go and stick with 32-bit for time being, but the steps are almost similar for the 64-bit as well. So the first, whenever the function is called, EBP and ESP are pushed, and based on the variable size and all these things, so your ESP is pushed downwards. Okay. So this is called a buffer size. So, and also every variable, for example, if you have a variable called name, so your name, if you keep inputting is uh, so, uh, so if you keep inputting s like this, you can actually rewrite your EIP. So name actually reads 10 bytes, but if you give more than 10 bytes and identify the point where you're able to rewrite your instruction pointer, then you actually hijack the flow. Now, in terms of A's here, you can run win function, which would execute the win function for you and give you the flag. So this is what the flow is going to be look like. And I felt in the last video, I felt I didn't mention a proper explanation for how the stack and all works, but I guess this should help you. So stack grows downwards and every details you enter goes upward, and your EIP or the instruction pointer is above your base pointer. So that's how you actually rewrite your EIP. Before that, if you want to learn more about assembly, I'll try to cover in the next video if possible, if you want me to cover assembly. So you have a very good resource by the Pond College. You can go through this, it's wonderful resource. And let's dive in. Just follow the previous steps. So we'll again use compile it with the 32-bit format, and G for the debugging. I'll tell you why it's useful. And no stack protector means there is no there's going to be no stack canaries and all, which we will, it's like a protection method for the buffer overflows and all, so we'll discuss more about that. And standard C99, just to bypass that gets and all that thing, because these functions are kind of you know bypassed. Like if you see, I'll just show you an example. So if you compile without this standard C99, you can see it just gives you an error. But for the demonstration purpose, assume that gets is not, and your OS is kind of vulnerable and kind of shift, then gets would actually do it. So this is how you do it. So just follow the steps in that. So I'll upload all my code and everything into the GitHub repo, so you can go there and check that out. Yeah, this is where I'll post my code. I guess I already posted it. So yeah, just go through and do it yourself. And the next part is, as I told you, you can do an object dump -d main. So you can see this is your assembly code, and there are two types of assembly codes here. Like the syntax should be simple. So we'll go here to this resource. I'll leave the link for this resource in the description below. You can go there and check that out. So there are like two types of syntaxes: Intel syntax and the AT&T syntax. You can see percentage here. If you see your this is your instruction, like move, add. There are like a lot of instructions: move, add, subtraction, and stuff like that. So here in the Intel, so the instruction is followed by the destination and the source, and in AT&T it's instruction followed by source and the destination. So this is a kind of reverse here. So, and also AT&T do have this percentage, and like most of the time this percentage symbol. So by seeing that, you can understand that okay, this is AT&T. And also one cool thing with object dump is you can actually provide this Intel architecture uh, through -m Intel. So now you can see your assembly code is in Intel syntax. So which makes it more easier. So destination followed by the source, and that's how things work. And so it's very hard to go through and read stuff like this. But assume that you only got your binary, and you can always do an object dump and see what functions are there. So these are like printf, gets. These are like basic functions which you load, and start and all these things. But if you scroll down a little bit, you can see the real functions that are there. So win function is there, which you can't actually understand what's happening through reading the source code, but that's the reason we enabled an option called debugging, which we will use later. And there is a read name which actually uses gets function. So through this you can understand which function is vulnerable in your binary. uh, and there is a main function and all that stuff. So we'll use something called as gdb. So gdb is not installed by default, I guess. So but most of the time it's installed on Ubuntu and all, but I don't know why. This is like my custom OS with settings. I mean, I disabled a lot of pre-built stuff of this Kali, so it won't work like that. So gdb is a very cool thing. So q so in order to run gdb over a binary, so just do gdb/main, your binary name. So if you do info functions, you can see all the functions here. And I would like to add something to the gdb. So if you want to make your gdb more advanced, you can use something called as gef, which actually more or less beautifies your output and debugging stuff. Like you can see all your variables, all those stuff. So it's very simple. So it actually creates a .gdb init file, which is like a .bashrc file for bash, which loads every time you open your gdb. So just copy this and paste it. That's it. Now just load the gdb again. Now you can see a gef terminal here. Now if you do info functions, you can see all the functions. As we enable debugging, you can see a separate section for that. But if your binary doesn't have debugging, then you would see your win function within this non-debugging symbols as well. So if you do if you want to see more about a function, there is something called disassemble win. and you can see what all instructions are present in your win function. And also by default, if you don't use gef or gef, you would see gdb outputting all your assembly code in AT&T syntax. So if you are comfortable with that, just go and use that. But I'm mostly of an Intel syntax guy, so I mean I'm doing this for quite some time, so that makes it that's very simple for me. And there are like some other options. Help, so you can see what other functions and all stuff like that. And you can simply one important thing is pattern create 200. So this creates a 200 bytes of pattern. So let's copy this and run. If you just run it, your binary is going to run. Just enter your name. Now you can see it actually got segmentation fault, which means there you actually rewrote your EIP here with AAGAA. So this is kind of pretty cool. Let me show you how it works. Let me copy this whole code. You can actually do a search as well, but let me show you how it works. And you can see what the value that is being written to the EIP, which is actually required for us, because if you rewrite that with that, that's going to be a simple. So you can see, let's delete all these things. I just control F and find out where this AAGA is. So, and you can also use something called pattern search, but I do like to do this in like a manual way. So it's obviously up to you. So I can actually give a couple of B's and let's see again. Okay, just run. Now you can see your EIP is going to be BBB. So I mean, this is just for like demonstration purpose. So now you can actually get the length of this. You can have something called as Python interpreter as well. Assuming Python is installed, yeah, you can see 22 bytes. So let's go back and rewrite our code. So we'll be using the same sys module again, which we used earlier. 22 and followed by the bin function. So now this is how the things work. But if you want to go step by step, this is not a recommended way. I mean, I just inputted like 200 characters and see where it's breaking actually. But it's better to do create a breakpoint. So breakpoint is something like if you run, so your code, your binary will run till where your breakpoint is set, and you can go from next like through different instructions. So most of the time you just do break main point, and if you do a run, you can see it shows you what's actually happening. And since the debugging is enabled, so remember the debugging is enabled, and you can see what actually is being happened as well. If your debugging is not enabled, you cannot see this code. So when you're in the learning phase, I would suggest doing this. So that then most of the time I would do ni, which is going to be the next instruction. So it goes to your next step, 1 2 3 4 for example. So and it actually seg faulted. So yeah, now again let's run it. Next instruction. Let me give only sufficient information. Okay. Now you can see what's actually happening. Next instruction, and again I got a segmentation fault. Let's do it again. Okay. So now next instruction, next instruction, next instruction, next instruction, and it keeps going. You can start seeing what's actually happening if you want to debug a lot. So this is going to be helpful. I mean, there were some challenges that I saw in some CDFs where you are extensively required to go through this next instruction phase to see what's actually happening. Sorry. So this is cool, but we identified where you need to rewrite and all. Now again, if you do disassemble, win function, you can see your win function's starting address, which is this. So just copy this, just paste it. So you can use pawn tools as well, but for the timing, I'll cover pawn tools. Pawn tools makes your life easier, but I'll cover about more about the pawn tools in the next videos and all. So let's me do a Q for the quit. So guys, there is a small issue with the win function here. So I just rewrote it and everything went well. So if I do a disassemble win function, you can see I get a new address now because there was some issue compiling, and also I'll write them in the readme of the challenge page, so you can go there and check that out. Now you can see the address here of the win function is this. So I created a python 3 using sys module, where I'm rewriting till EBP, and then I'm rewriting the RIP with this value. So this is the little Indian value. So little Indian in the sense like every value will be in the reverse format. So it's going to be 86, 91, 04, and 08. So that's how it is done. So 86, 91, 04, and 08. So in x86 format, in x86 the addresses are mostly in this little Indian format. So you don't find it like this. So it's going to be in the reverse format. So there is something called as pawn tools, so which use something called as p32 of, if you provide this address, it automatically does this for you. But for the time being, let's use this like this. So this is called little Indian format. Don't get confused. So all your bytes are going to be in the reverse format. So if I do quit and if I run this module, you can see your flag here. So the buffer overflow exploit. So what we done, I'll give you a quick grasp on what we done. So we rewrote all the buffer and the EIP with the win function. So all this is write till EBP, and then the next value is going to be in your EIP, so which is going to be the win function within a little Indian format. So you can just go through the little Indian format and you can identify what's actually happening there. But that is it for today's video, guys. I hope I've covered something useful and important. If you have any doubts, feel free to reach me out on Discord or through the comment section. And check out this the resource page on of this challenge. So I'll leave the link for the GitHub repo in the description below. So go there and check that out. This is Satvik. Thank you for watching this video till the end. Take care. Bye.